Now let's look at the range of floating point numbers. In the previous class, we looked at this template called std and numeric underscore limits. It's part of the limits file. So if you include limits, you will be able to use this template. Here we will call this template with float, and we will query what is the maximum, lowest, and the minimum. Now notice I've changed the notation for printing. Previously it was std : fixed, which means we were printing all the decimal numbers in the fixed mode. Now we want to change it and print the decimal numbers in scientific representation. So when you do std cout followed by std : scientific, the floating point numbers will be printed in scientific form. So let's look at what is the maximum float, minimum float, what is lowest float, and what is minimum normalized float. So we will come back to what is the minimum normalized float at the end. For now, let's execute the code and let's look at the values. Similarly, let's look at also the range for double or 64-bit double precision floats. So let's continue. Now notice the maximum float is 3.4 times 10 to the power of 38. Minimum float is minus 3.4 times 10 to the power of 38. Lowest float is again minus 3.4 times 10 to the power of 38. Our minimum normalized float is 1.7 times 10 to the power of minus 38. So what is the difference between minimum normalized float and the lowest float? So the minimum normalized float is the smallest positive number that can be represented using 32-bit single precision floats. So the smallest positive number after 0 is 1.17 times 10 to the power of minus 38. However, the lowest possible float that can be represented using 32-bit float is minus 3.4 times 10 to the power of 38. So if you want the lowest, you will need to query using std numeric underscore limits : lowest. And if you want the smallest positive number, you can use numeric underscore limits : min. Now with integers, we saw that any number greater than the maximum allowed number that can be stored within a data type would cause overflow. Here there are two issues with floating point numbers. Any number that is greater than max will cause an overflow, and any number that is less than the min will cause an underflow. So any number that is less than the smallest positive number that can be represented will cause an underflow, and C++ will handle it in a different way. So the way C++ handles is known as subnormal. I will not go into details, but if you're interested, you can look up what subnormal representation is. It's pretty simple, so we will not actually dwell into details, but I just wanted you to know that even numbers less than the minimum numbers can be represented in C++, but they use a different format. Now similarly with doubles, we have 1.7 into 10 to the power of 308 as the maximum double. Minimum double is again minus 1.7 times 10 to the power of 308. And the smallest double that is greater than 0 is 2.2 times 10 to the power of minus 308. Now let's switch to a different topic. We saw previously with integers, we can cast between different types. We can cast from an unsigned int to a signed int. We can cast from an unsigned long to a long, and things like that. Here we will see what happens when we do the casting with floating point numbers. So first let's declare a float f and initialize with value 12.614156. And let's then cast it to an integer and store the result as an int. Now let's look at what will be the value that will be printed when we print f and I. So let's continue the code. Okay, now notice f is equal to 1.26. So it's now represented in scientific notation, and I is equal to 12. So what happens here is we are discarding everything after the decimal point, and only the integral part will be printed. So I only has the integer part, which is equal to 12, and the decimal part is just discarded or truncated. Now instead of that, if we want to do something like adding, let's add 0.5 to f and then store the result back as an integer. Now this should give us a compiler warning. So what we are doing here is we are adding 0.5 f to a floating point number, and then the result is implicitly converted to an integer. So this implicit conversion should throw an error, should throw a warning. So right now I think the warning level is 3 in my code, and therefore I'm not looking at it. But if we change the warning level to 4, we should get a warning here which says that you're converting from a float to an integer. So there should be a loss in accuracy. So now let's look at the output. Now notice after we add 0.5 to 12.6, the result is greater than 13. So we're only looking at the integral part of the result. Now going the other way should be okay. So that is when we initialize an int with 15 and then cast it to a float, the result should be okay. So when we print f and I again, notice I is equal to 15 and f is exactly 1.5 times 10 to the power of 1. However, is this always the case? That is, when we have a bigger number, like a bigger integer here, 987654321, what happens when we cast this to float, and what happens when we cast it back to an int? Right? So let's first look at what happens when we cast an integer to float. Notice I is still 987654321 and f is 9.876543, so it's only accurate up to 7 decimal digits. After that we have 36 times 10 to the power of 38. Now if we cast the float back to an integer, let's look at what happens. So in line 74 we are casting f back to an integer using static underscore cast, and the result is the integer is 987654336. So notice when we cast from an int to float back to an int, we don't get this original int that we started with. We're getting a different integer value. So we need to be again careful when we are dealing with larger numbers. Issues like casting an integer to float and back to an integer may not give you the same value. So it's good to think about these problems when you're writing code with C++. So certain things like these are obvious when we are working with real numbers. We know that a real number, when we truncate it to an integer and go back to real, it's the same. But this is not the case with floating point numbers. So we need to be extra careful when we are dealing with 32-bit or 64-bit doubles in a C++ program. Now let's look at what happens when we cast a double to float. So we know double is 64-bit, float is only 32-bit. So the number that will be saved, the result that will be saved when we cast a double to float will be either rounded to the next highest possible floating point number that can be represented, or it will be rounded off to infinity. So here we are declaring a double d which is equal to 2 into 10 to the power of 10. Then we are casting it to float using static underscore cast. So let's print the result. Okay, now notice the number can be exactly represented in both float and a double. So even though we cast from a double to float, we are not losing any accuracy when we have a small number. However, let's increase the number from 2 to the power of 10, 2 into 10 to the power of 10 to 2 into 10 to the power of 145. And let's look at the same operation. We are casting the double to a float using static underscore cast, and let's see what will be the output. Okay, now notice even in double we will not be able to exactly represent this big number, and in float this is now rounded off to infinity. So what this means is when we switch from 64-bit to 32-bit representation, there is no number that can be that can approximately represent this 64-bit number. So the the number is rounded off to infinity. Now let's look at some special numbers with doubles. Previously we saw that division by 0 with integers would lead to unexpected behavior in C++. Now let's look at what happens when we do this with doubles. So here I'm initializing a double with 0, and then I'm doing 1 divided by 0, 1.0 divided by 0, minus 1.0 divided by 0, 0.0 divided by 0, and then I'm taking sine inverse of minus 2. We know that sine has only values between minus 1 and 1. So what happens when we take arc sine of minus 2? So let's print these values and let's look at the result. Okay, so the first one was 1 divided by 0, which is equal to infinity. Minus 1.0 divided by 0 is minus infinity. 0 by 0 is nan. And arc sine of minus 2 is again nan, or not a number. So previously with integers, we were not able to do this. We will get an exception, or we don't know what would be the behavior of the code when we divide by 0. With floating point numbers, they are represented using special numbers, which are infinity and not a number. So let's look at what infinity is. So let's print infinity using std numeric underscore limits. So we saw previously a 32-bit floating point number has 1 sign bit, 8 exponent bits, and 23 bits of mantissa. When all the 8 exponent bits are 1 or 2, so the value in decimal is equal to 255, and when mantissa is all 0, then that number will be represented as infinity. Now when all the exponent bits are 1s and the mantissa is non-zero, then such a number will be represented as nan, or not a number. So let's print what is a infinity. So here again std : numeric underscore limits, double is the data type, : infinity prints the value of infinity. Okay, now notice plus infinity is inf, minus infinity is minus inf, and not a number is nan. So again, you don't have to assume what these are. You can just use std numeric underscore limit, query what is infinity if you want to check whether a number is less than infinity. So for example, when we do division, we want to check whether the number is less than infinity, or when we cast from a double to float, we want to see whether the cast failed or not. If the cast failed, the number will be infinity. If the cast worked, the number will be the closest approximation. So next, let's look at some arithmetic with nans. So here I'm adding 10.0 times 0.5 plus 3.0 plus nan. So let's see what happens. Will the result be still not a number, or will the result only do the arithmetic before the nan? So let's continue. Notice 10 times 0.5 plus 3 plus 9 is equal to 9. So if you add not a number to any other floating point numbers, the result will always be a nan. And the final thing that we want to check is whether nan is equal to nan. So can we do this? Can we compare two nans or not? So here I'm checking whether nan is equal to the same thing, nan. So let's print this. Now notice nan equal to nan is equal to false. So which means we will not be able to compare two nans. If you want to check whether a number is nan, you can use what is called as std : is nan. So if you pass a double to is nan, you will get a result either true or false based on whether the number is equal to nan or not. So don't use equal to operator to 1 compare two floating point numbers, and don't use equal to operator to compare whether a number is equal to nan. So if you want to check whether a number is equal to nan, you should use std : is nan. So this completes the module on floating point numbers. In the next module, we will pick up with functions. Thank you.